Introduction to Three-Dimensional Vectors. This is Year 13 Pure Maths. Okay, so in Year 13 we have three-dimensional vectors, which is not a lot more complicated than the 2D in terms of the course content, because it really is very much an introduction to this. So don't freak out too much. You don't need to visualize too much either, so don't worry. What I've got here is a cuboid in 3D space. So we've got A, B, C, D is the kind of front of the cuboid that you can see, and then F, G, and H are vertices that again you can physically see, and then E is at the back, you can't physically see it, but I've labelled it, and then the dashed lines are edges of the cuboid that you can't see. What I'd like to just introduce first is just three-dimensional Pythagoras. Now you may or may not know that this is true, but I'm going to prove it to you anyways. And three-dimensional Pythagoras is looking at, well, what length is that line? Now this line that I've just drawn on, this is a pink line, this is what we call the long diagonal of the cuboid, and it goes from one vertex of the cuboid, which is A, right through the middle of the cuboid and hits its opposite vertex, G. And well, what is that length in terms of the edges of the cuboid? So let's call this length, let's call it A, let's call this length B, and let's call this length C. It doesn't overly matter. What is the length AG in terms of AB and C? Well, let's just first consider a simpler problem. Let's first of all consider this length here, AH. So AH is another diagonal, but it's not the long diagonal of the cuboid. It is the long diagonal of the triangle, of the rectangle AEHD. Okay, so it's the base of the cuboid. And we can say by Pythagoras that the length AH must equal B squared plus C squared square rooted. So it's the square root of B squared plus C squared. Okay, that's just Pythagoras in 2 dimensions. Well, we can use that to calculate this length here. So if you consider this right angled triangle, A to G, G to H, and H to A, because this is a cuboid, GH and HA, they are perpendicular. So that is a right angled triangle. It's just in 3D spaces. It's very well embedded into 3D space. But we can still apply Pythagoras to it. It's still a 2-dimensional right angled triangle. So we know that AG squared, or AG, is the square root of AH squared plus this height here, which is A squared. But we already know that AH is that thing, so if you square it, then we'll get the square root of B squared plus C squared plus A squared, or if you like, A squared plus B squared plus C squared. And that is 3-dimensional Pythagoras. Okay. It's still the square root, don't cube it, and it is still the sum of the squares. It's just you've got 3 numbers now instead of 2. So if you want to find the length of a vector in 3 dimensions, okay, bit of notation, cool from first year, the magnitude of the vector is equal to the magnitude of, let's say the vector is, let's go with V1, V2, and V3, where these are numbers. And we want the magnitude of that, then we just apply Pythagoras to it. So it's the square root of V1 squared plus V2 squared plus V3 squared, all square rooted, where V1, V2, and V3 are just numbers. Okay, so that's a 3-dimensional Pythagoras. Okay, so I've hinted at here what the vector in 3D looked like. We've got 3 components now. We have an X direction, we have a Y direction, and we have a Z direction. And this vector here is what we would refer to as column form of the vector. But there's also component form. So column form, this looks like a column. This is V1, whatever number that is, in the X direction. v2 in the y direction and v3 in the z direction. And that's what we would refer to as column form. And a question can give a vector as a column, but it could also give a vector as component form. And component form is v1 times I plus v2 times j plus v3 times k. This is component form. They are exactly the same vector. Okay? Whether it's given to you in component form or in column form, you can do the working in the other. It's not a problem. You just choose your preference. It really makes no difference. Notice it's very similar to the two-dimensional one. It's just you've got this extra k. So in 3 dimensions, the vector I is the unit vector in the x direction. That just means 1 in the x direction. The unit vector j is 1 in the y direction. And now we have this new one, which is unit vector k, which is a unit vector in the z direction. So that's the definitions of I, j, and k. What we can do with vectors is we can find the angle of a vector with an axis, either an x-axis, a y-axis, or a z-axis. Now in 2 dimensions it's quite straightforward, because in 2 dimensions you can just think, okay, well, let's draw my vector from the origin and let's think about what triangle that makes. So we're going to have a distance here, which would be the y component of the vector. Let's call it v2, and then we'd have a distance here is v1, and then we could use the magnitude of the vector as being that length there, and a little bit of SOHCAHTOA will eventually arrive you at the correct angle theta, which you could say is the inverse tan of v2 over v1, or you might have the inverse cosine of v1 over mod v. Or even the inverse sine. And the reason why I put that bottom one in is because that is exactly the one that we use in 3 dimensions. But it's much easier to just consider it as the as a rule. So here, to calculate the angle between our vector v and the x-axis, we took the x component, which was v1, and we divided it by the modulus of the vector v, and that gave us the cosine of the angle, or if you like, if you inverse cos it, you'll get the angle itself. Exactly the same is true in 3 dimensions. So if you want to find the angle of the vector with the x-axis, you would inverse cosine the x component, which in this case is a, divided by the modulus of the vector, modulus of v, okay, which would be the square root of a squared plus b squared plus c squared. Or if you wanted the angle with the y-axis, we would do exactly the same formula, except instead of using the x component, we use the y component. But we still divide it by the modulus of v. And finally, if you want the angle with the z-axis, then you would do the arc cosine of the z component of the vector divided by the modulus of the vector. Okay. So a quick example. Let's say v is the vector 4, minus 3, 5. And we wanted to find the angle of that with the z-axis. Then this is going to be the inverse cosine of 5, which is the z component, divided by the square root of 4 squared plus minus 3 squared plus 5 squared. It's a modulus of v. Let me just pop it into the calculator. Usually we stick with degrees mode. So angle unit in degrees. And we want the inverse cosine of 5 divided by the square root of 16 plus 9 plus 25. Yeah, it does. It comes out very nicely. It's 45 degrees. Okay. Or if you wanted the angle with the y-axis, we would do arc cos of the y component minus 3 divided by the square root of 4 squared plus minus 3 squared plus 5 squared. Again, pop that into the calculator. Change that to minus 3. And I get 115.1 degrees. That's bigger than 90. If you think about it, a vector will have two angles, won't it, with an axis. So we're looking at the y-axis. This vector's down here. There's my y-axis. There's my v. And what it's done is it's calculated this angle here, which is 115 degrees. So if a question has asked for an acute angle, then we might need to correct that and say it's actually 180 minus that. So if I do 180 minus my answer, I get 65 degrees, or 64.9. So just make sure you're reading the question, okay? If it asks for the acute angle, then you need to subtract it from 180, or you can just mod the minus 3. That also works. Okay. So that's it for this video. I'm going to do a couple more videos on year 13 vectors. So please watch those, and hope you enjoyed it and learned something.